Hello and welcome back to my channel. So we're going to be talking about the nth term test for divergence, which comes from a theorem that's not even about divergence. So we have this limit of the nth term of a convergent series. So if we have the summation of our sequence's terms, so from n equals 1 to infinity, and it is converging, then we know the limit as n approaches infinity of the nth term of that sequence. So as we get towards infinity of those sequences terms are going to end up equaling 0 as we go towards infinity. So if our sequence is converging, then we know that those terms, as we go towards our infinite term number, is going to be 0. So one thing to note is that that's not always true the other way around. Just because the limit is going towards 0 doesn't always mean that we are going to converge. And the best way that we can show that is by using this thing called the harmonic series. And the harmonic series is a series that we're going to talk about in just a little bit. It relates to a series that we're going to look at in just a second. But it is the summation from n equals 1 to infinity of 1 over n. This right here is called the harmonic series. It's a really important series, and it is one that was so important that they decided to give it a special name other than like what the name of what we would be looking at it is. This limit goes to 0, but it diverges. So if we look at the terms as we go towards infinity, 1 over a really big number goes to 0. But as we looked at the series as a whole, when we add more and more and more of them together, we found out that it's just going to keep getting a bigger sum. So our series diverges. So limit goes to 0, but diverges. So that seems like it's not going to be very helpful. If we can't say if a limit is approaching 0, then it converges, then it's not very helpful to what we want. But one of the things that you may remember is that we're calling this the nth term test for divergence. So even though we can't say the limit approaching 0 automatically means that it converges, we can say one other thing. So if the limit as n approaches infinity of our sequence's terms. So if our sequence's terms as we go towards infinity are not equal to 0, so if our terms don't end up kind of petering out to nothing, then we know one very important fact, and that's our sum from n equals 1 to infinity of those sequences terms, it's going to diverge. So as long as our terms don't go to 0, we know our series as a term, if we keep adding stuff to it, is going to diverge. And that makes sense because if my terms don't go to 0, then it would be like if I added 1 forever. It's never going to give me a solid number that we're dealing with. So we're going to use the nth term test for divergence to kind of help us out. This is one of those tests that you hope that the limit doesn't equal 0, so then you can be done. You know it diverges, and you can give that answer. So that leaves us with one really important fact, which is, what do we do if we don't know it converges, but we know that the limit goes to 0? So what happens if the limit does go to 0? What that means is that it's like indeterminate form. So we have to try something else. And that's the biggest part of this unit, especially at the beginning, is just learning these different rules to test for convergence or divergence. We might not always find what it equals to, but knowing if it converges or diverges tells us information about what we're dealing with. So just like indeterminate form, if we get that the limit does equal to 0, we can't really say anything else, so we have to try a different test. So what we're going to do is we are going to use that nth term test for divergence and decide if our series diverges or if it's inconclusive at this moment in time. So if we look at what we have here, we have the summation from n equals 1 to infinity of n over n plus 100. One of the things that you may have noticed is that the limit as we approach infinity of a sub n is the same thing that we're adding. So the limit that we're looking at is the equation they gave us. So we have the limit as n approaches infinity of n over n plus 100. This is where we're getting into our limit towards infinity things again. So this is Botno, Bobo, and Eats DC. This is our exponents are the same situation. So our degrees are the same on top and bottom, meaning we need to look at the coefficients. Coefficients are 1 over 1, so we know this is going towards 1. It's not going towards 0 because 1 does not equal 0, so what we know is the series diverges. This is nice because we can be done. Okay, now if we look here, we have the limit as n approaches infinity of 1 over n squared. One of the things that we can kind of do here is remind ourselves that 1 over n all squared is the same thing as 1 divided by n squared. As we get really, really large numbers in the denominator, our function overall is going to go towards 0. Because our limit is equal to 0, we are inconclusive. We don't really know what to do next. And because this is not a geometric, it's not something to the nth power, we don't really have anything else we can do. So for right now, this kind of just stays where it's at. The limit as n approaches infinity of 1 plus 3 to the n over 2 to the n. So once again, we're looking at the function's behavior as we go towards infinity. 3 to the n and 2 to the n are what we're going to be focusing on. That plus 1 doesn't matter. 3 to the n is a bigger function. It's going to grow faster than 2 to the n. So we know that this is going to be going towards positive infinity. And because it's not 0, the series diverges. And then this last one. So if we look at the limit as n approaches infinity of n cubed over n, this exclamation point. Now, some of you may have never seen this exclamation point before. Some of you have, especially if you've taken statistics at this point. So we're going to take a little bit of a deeper dive into this because some of you, if you don't know what that exclamation point is, won't know what to kind of do with it.